My name is Abdulahi,
And I'm Ahmed.
and today we're going to be talking about scaling Android development without a monorepo. Now, as a disclaimer, this talk isn't about monorepo versus non-monorepo, because both of them have their pros and cons. But one of the things that's required with a monorepo is a dedicated DevX team to help you with things like VCS handling and build support, right? When you think about something like building a subset of the project, of the monorepo that you actually want to work with, right? And this comes at a cost, and smaller to medium companies might not be willing to pay that cost. So just a disclaimer. So I work at Kareem, and if we go back to Kareem's initial days, we started off as a ride-hailing app. And back then, it was rather simple. We had one repo that shipped out one ride-hailing app, and it was as simple as it could be. Until one day, the company decided to invest in a food delivery platform. And in that case, we followed a similar format of ride-hailing. So we're like, hey, let's just build out a food delivery app and ship that out too. But when we got to that point, we were like, why don't we share some of the smaller UI components that we have in the ride-hailing application that we have already, and share them with the food app. And back then it was relatively simple because food and rides were completely separate. So both of them could adopt the latest versions of this UI component at their own pace. And whether there was a breaking change or not didn't matter, because it was up to the app to adopt this change. But this changed overnight when the company decided, hey, we don't want to ship two separate apps anymore, but we want to ship out one app, one Kareem app, that kind of has everything that Kareem has to offer. So then we had to explore the option of, or how to merge two applications into one. And this made things complicated overnight for us. So from a high-level approach, the approach that we took was, instead of shipping out two APKs to the Play Store, we kind of just shipped them out as AARs into one application, treated them as libraries, and then shipped that application out to the Play Store. So for more information of like how we made this possible, you can check out Ahmed's talk on how to build a super app. But for the gist of it, we started coining rides and food, in this case, as mini apps, and the application that shipped to the users as a super app, given that these two were actually previously apps and we just turned them into smaller apps. So to be clear though, mini apps are really just groupings of features, right? If you think about food, for example, what does food entail? You can look for a restaurant, you can browse a restaurant, you can check out, and then you could probably track your order, right? And every single one of these are features. So a mini app really is just a grouping of features. Any feature AAR that's shipped out to an app can be powered by a single or multiple repos. It doesn't have to be solely confined to a single repo. And in our case, for example, we had multiple repos kind of combining into a single feature AAR that we shipped out to our super app. And one thing to keep in mind is that every single repo that we had its own release cadence. So any one of them could release at any point, and they would just bundle up into the previous feature that was shipped and ship out again to the super app. So if we look at it from a high level, we had multiple features being contributed to n number of repos being shipped into the app. And to us, that was the container, right? So all of these repos would ship into the container, and then we would then build this container and ship that into the Play Store. But what is a container? A container really is just the app shell. The only thing that it's responsible for is, one, of course, it lives in its own repo, and it's responsible for kind of grouping all of these features, and it also delegates to them. So it outputs the final APK that's generated once we group all of these features and ships it out into the Play Store. But to make this possible, we needed to define a set of architectural principles to follow to make sure that we don't break things down the road.
So some in place before we started actually building something like this. The first was no feature directly depends on another. And if you think about this in practice, you have a set of teams working, for example, on a set of food delivery features and another set of engineers working on rides. If you have direct dependencies between them, you make life very complicated for many reasons. So for example, let's say that you work together to release a new version. So you release a new version of food and rides, and then suddenly you realize that like, oh, there's a bug in this version of rides. So you want to roll it back. Now, do you also need to roll back food, or is it okay, or is it not? And you become in these kind of questionable states. So we wanted no direct dependencies between features and each other. This enabled us to have a second thing, which is that features are optional. And I say terms and conditions apply because in general, any feature grouping like this, we can enable or disable. But there are certain core features that you never allow to disable. Something like the login screen, or the or identity and the token for the customer, and so on and so forth. Some critical things like that are always there and cannot be disabled. And finally, we had an aim of like not repeating ourselves. So now you can imagine, as you have more and more engineers, right? This is also the company scaling up at this point in time, and now we have, from 10 engineers, now you have tens of engineers. And then you start saying, okay, I don't want the people in food to be reinventing the wheel of what the people in rides are doing, and so on and so forth, right? Because otherwise, things become pretty messy. So I don't want 10 ways of doing, analytics, and 10 ways of doing experiments, and so on and so forth. So with these in mind, let's start figuring out like what kind of interfaces we could have that represent something like this. And the surprising thing that I will say is that these interfaces are actually quite accurate compared to actually what we have today. They're not that much different. Maybe there's additional stuff there, but in general, this is the bare bones of it. So you have a feature factory that, given a dependencies provider, which we'll get to in a second, returns a feature. And today, this feature, let's say, is just empty. We don't have anything there. And the dependencies provider holds all the dependencies that the feature might need. So things like analytics, experiments, and so on and so forth, that are used. And so these interfaces are what the actual features use directly in order to work. So if I'm working on a feature team and I need analytics, I say I have a dependencies provider object, give me the analytics provider, and then .log analytics with whatever I'm logging. Same thing for location, same thing for all of these things. Okay, so then the next question becomes, okay, we're talking about interfaces now. Who implemented these interfaces? And so that is the responsibility of the container. So the container implements the dependencies provider, and the nice thing about this is the underlying features don't care and don't need to know what the underlying implementation is. So what is being used for analytics, it's not something important for them to know, nor do they need to know. And we can change things dynamically, and as long as the API is consistent, we don't need to make any change to the vast majority of the features. And so visually speaking, the container implements the SDK, then it depends on and provides SDK implementations to the features, and is responsible for outputting the APK. So one pretty interesting note about dependencies provider that I think that actually shows that this is actually a very powerful pattern, because it's an interface, and because the features are all just relying on the interface, irrespective of what the implementation is. It gives us the ability to wrap it, or no-op it, or replace it. And we actually use this for some really critical things. So for example, you can imagine for non-Google Play services, you have non-GMS builds, for example. You can swap the locations provider from using the fused provider of Google to using just the GPS on the device, for example. And then none of the underlying features need to update their code, and everybody's suddenly GMS compliant, for example. We actually even use this for things like UI components, the maps implementation. So in some cases, we would ship Google Maps, and some cases we'd ship Map Libre, for example. And then you could kind of swap between them at compile time and say, hey, and without needing to change the underlying implementations. And also for wrapping becomes very powerful for development. So one of the things we did there is like analytics events, we would log them and show them in a screen. Here are all the analytics events so that the developer can kind of validate. Similar things, override these experiment toggles, things like that. No opping so that you don't go to the production one and so on and so forth. So let's take an example, just a practical example. Let's say navigating. And so we use deep links for navigation, both internal and external. And so to do this, we kind of put a schema for ourselves that we'd have something like, okay, scheme : // which is usually the name of the company or something like that. Feature ID, which is kind of a routing ID, so as to which feature can handle this particular deep link, and then the actual parameters that we passed in after that. Then we have an interface for a deep link resolver with just a single method called resolve that, given a URI, may or may not return an intent. And this was, the other thing you have to realize is these Android apps have been being built for a long time. So there's still multiple activities. It's not a single activity architecture and so on and so forth. So this was the most suitable things. But this same thing would work for Compose, for example, because I could just as easily as in returning an optional intent to return an optional composable function, for example. We go back to our feature interface, which had nothing in it, and we say that every feature could optionally opt into saying, I will give you a deep link resolver, which could resolve deep links. And now we can put it together. So the container receives the deep link, because you can only have one place to receive, one central point to receive things like deep links. So you receive it in the container, you parse the host, which is kind of the routing key, and then you say, hey, given this list of features, give me a feature, if one exists, that says, hey, I can handle this routing ID. And if so, if it has a deep link resolver, resolve the URI and return it or return null. And the nice thing is the container here can say, hey, if it's null, do this fallback behavior. Don't crash or do something else and so on and so forth. And that's also what allows the optionality principle that we talked about are the principles. So I mentioned the features. Where do we get the features from? And we call this registration. And this is just a simple map. It's a map between the routing ID and the name of the factory. Very early on, we used to handwrite this. And then eventually we wrote a KSP for it to automatically code generate it based on annotations on the factory classes. And the nice thing about this, though, is what this enables is the container in the registry module just has something like this. That's how it includes rides, and that's how it includes food. And so if I'm working and I don't need to build rides, I can just comment it out. And I don't need to make any other changes to the code. The code will build fine. And same way I can add a Gradle property to say, hey, only build this subset or this, and so on and so forth. No other changes are required. If you think about push notifications, exactly the same thing. The container receives it based on some key. It routes it to whoever is best suited to handle it, and that's it. So, okay, great. So how do the teams actually develop? So we had this diagram of saying that, hey, teams have their own set of repositories and output an AIR, and this AIR, the versioning is read by the container, and that's kind of how it works today, right? So if I'm working on a feature, what do I do? Maybe the first most obvious answer would be Maven local, right? But it's a bit painful, because that means that me as a developer, I need to push my changes to Maven local. Then I need to go and open probably another Android Studio project that has a container, bump the version of the dependency to the snapshot version, then build and test, and oh, I have a bug, and I have to go back, and it's tedious, right? So instead, what we decided to do is librarycize the container, inventing words here. But so if you think about it, the container is a subclass of the application class, sorry. And it's that and some other things. So we can actually just bundle those themselves into a library that we push to Maven or Artifactory or whatever. And the feature teams themselves can actually depend on that during their development. And so the feature teams introduce an app module, which is their own kind of copy of the container. They can, and because we publish this once a week, so they're at most 1 week behind whatever the actual thing that's shipping into production is, and this code doesn't change much. But so that to make the development environment as close to possible as to production as we can make it.
So with all the moving parts that we have over here, CI/CD becomes a really crucial aspect of making sure that everything works as expected and also smoothly. So when you think about things like how all of the features themselves work together, and also making sure that the features ship to the final app smoothly and like a train, basically. So what does CI/CD entail for something like this? So the first part would be sharing the steps. And this is mostly because of two things, right? One is that every time a team creates a new repo, 90% of the time the steps remain the same, whether it's building, UI unit tests, and so on. But also making sure that it's standardized across all the features to make sure that every single feature is kind of running the same kind of checks and going through the same checks as well before they finally come and ship to the final app. So what do these common checks really look like? So we have a bunch of examples here today. And to start off, we'd have our dependency diff. Internally, we use Renovate, for example, to bump our internal dependencies, whether it's third-party or even internal feature AARs to our final app. So an example like this would be coil. And the nice thing about dependency diff as well is not only will it catch the dependency that you're actually bumping, but also all the transitive dependencies that are bumped as a side effect. So this screenshot is an example of bumping coil to 2.7. And as you can see, the first 4 dependencies are coil, but then it transitively bumps Kotlin's standard library as well to 2.0, which was caught over here. And you can do further checks along this to make sure that you block a PR that has any side effect, or so on and so forth. You can tailor it to your needs. Another one would be size delta difference. So this is pretty important because when you think about the final APK that's being shipped out into the world, you have a bunch of different feature AARs that are being shipped to your app. And the number of features that are being shipped are growing as time goes on. And you want to keep the size of your app as small as possible so that it'll automatically be downloaded every time an update goes out. Because once you hit a certain threshold, it's not going to be downloaded, it's not going to be updated automatically. So 2 things to catch over here is like when you're bumping your internal dependencies, things could slip through. For example, you accidentally added some PNGs or a lot of different assets which increase the size of your final build by a lot. And you could catch it over here. But you could also catch third-party dependency bumps that drastically increase the size of your app as well. So one nice thing about this is, like I said, we use Renovate as a tool to bump our dependencies internally. And given all the checks that we have on CI, once these checks pass, then we automatically merge the PR. But if checks like this fail, then we could print out a failure report and block it from automatically merging with something like this. So that one, for example, breached. This is an example of something that breached our SLA, and this would require a manual review to pass. So then someone from the platform team could go through the code, see what changed, and if it's acceptable or not. Another rather important one is a manifest diff. And it doesn't sound like much, but this is actually quite painful in a lot of cases. So what this does is, after we've merged all of our features into our app and we have that final merged manifest, we want to make sure that no permission is being snuck into the app without us knowing. And this could hurt us once we're shipping to Play Store. An actual example that we had is that we bumped a third-party dependency, and this third-party dependency had a permissions of feature. And it kind of said, hey, our app only runs on phones that have actual cameras, which screwed us over once we got to the Play Store. And this was a check that we added after that to kind of make sure that something like that never happens again. So this kind of checks against the permissions added from third-party libraries as well as our internal libraries. And finally, we have source and binary compatibility. And this applies both to our internal and third-party libraries. So I'm going to start off with source compatibility since it's the more straightforward of the two. And source compatibility is mostly when you break the public API explicitly. So this is an example of our feature interface where you provide a location item. And initially it was just a pair of doubles, and we changed that to a location item. Now, once you try to ship that out and compile it, it'll fail at compile time. But the sneakier version of that would be binary compatibility, which would fail at runtime instead of compile time. So how would that look? If we use the same example and we have location item, which is just the longitude and latitude, and we have our feature interface, which provides a location item. Feature A implements it, provides a dummy location item, and then in main, we build a feature, we get the location item, and we print it. Straightforward there. So let's compile all of this. So I've compiled feature implementation here, which is just feature A and main. So here is just a list of generated classes from the compilation. And once I run main, then I get the printed location as expected. But what if I decided that every feature now needs to provide its ID? And given that I want to make sure that I don't force everyone to have to provide the ID, I just gave it a default. And in my head, I'm like, hey, since it has a default, then feature A shouldn't need to implement this. So in this case, then I just ship that to main, try to get the ID and print the ID. To mimic that, I only compiled feature and main. And I did not recompile feature A because I didn't see a need to. The provide ID function already has a default. But once I tried to run main, it throws an abstract method error because feature A can't find any reference of this provide ID function. And this is because, well, feature A compiled against the first iteration of feature, and main compiled against the second iteration of feature. So main has a reference, main compiled against the second version, so it knows the provide ID function exists, but feature A's never seen it because it's only compiled against the first version. And then once it tries to run it at runtime, then it crashes. So one thing to keep in mind as well is that Gradle will compile every single module that you have within your own repo. Let's ignore other libraries that you use, but within your own repo, it's going to compile every module against the stated version in that module. So if you have multiple modules with different versions of a library, it's going to compile against the version that you defined in the library. But then for packaging and runtime, it's going to take the latest of all of those modules and try to use that. So in that example, you could actually have a binary compatibility issue within your own project. So there are tools that can help you catch this. There's Kotlin's binary compatibility validator, and then there's also Google's Mentalog. And both of them operate similarly, in which they spit out a .text file with your public API. So one thing to keep in mind is that you could have the same issues, the same binary compatibility issues come from your third-party libraries. So third-party libraries can just as easily give you binary compatibility issues once you bump on one of the features or maybe just the app without the rest of this. And this poses an issue for us as well, because catching this at compile time is also it's tricky. You can't do it. So one thing we decided to do is think a little bit or start to look a little deeper into dependency and how we kind of operate with dependencies that we have in our app. And with that, we started to look at segregating dependency ownership. So we have, in that case, we divided all of our dependencies into platform dependencies and feature-specific dependencies. So platform dependencies would be dependencies that both either platform wants to control or dependencies that are used across multiple features. And feature-specific dependencies would be dependencies that's used by a specific feature. So an example of a feature-specific dependency would be, let's say feature A decides that it wants to do something with a video, and so it needs an Expo player dependency. Given that no other feature uses it, it becomes a feature-specific dependency. But then tomorrow, if feature B says, I need to do something with the video too, then Expo player now graduates into a platform dependency. But now that we've defined what a platform dependency is, we're trying to say that platform would control the versions used for those specific dependencies. But how do we control that? With that, we have dependency alignment. And the idea behind this is that platform themselves would have their own bill of material or version catalog. And in that case, they would define, of course, define all the versions internally and centralize control of these dependencies at a platform level. And then at the end of the day, they would spit out or publish the bill of material or version catalog used. Both of them have their pros and cons, but both get the job done. And of course, at the end of the day, only the platform dependencies are published in this manner. So what are the challenges that we kind of faced with this?
So some of the challenges of this approach compared to, say, the Monorepo, some of the Monorepo approach, it becomes more difficult to make changes across the app. So with a Monorepo, for example, if I need to change, let's say I want to change my SDK, I want to add something to feature, or I want to change something in feature, I can easily grep the code and figure out, okay, like here are the things I need to change. I change them one shot, it builds, it compiles, it works. But now that the development is distributed across tens of repos, it's much more difficult. And so deprecation, for example, of APIs becomes much more tricky to make. And typically we end up having to do things like we have code search that we go find all the usages to see who's using it in the first place. If no one's using it, you can just remove it. But if someone is using it, then we need to have a backward compatible way of handling it. And so to use an example of the ID example that Abdullahi gave, you can actually make that work by having a marker interface, which is just an empty interface. And if you implement that interface, then you have that method. If you don't, you don't. So you do tricks like this, and then you mark it as like, hey, I deprecated this in this release, and I can remove it in this release, and you kind of, it takes time to deprecate things. And another challenge is if you want to extract a standalone SDK, it's tricky because now a lot of your code is coupled to this idea of I get a dependencies provider with all my dependencies, and that might not be the best thing when I'm trying to output an SDK for the world to use, for developers to use. Thank you, and I do have a poem as usual. So for smaller teams, for some smaller teams, having DevX is a distant dream, but they can continue to scale until their code base is as big as a whale, ignoring the monorepo reviews, multiple repos they will use. One main repo controls the release, version bump PRs will certainly increase. Since every team builds on their own, tests and makes sure it works on their phone, uploads their new version to internal Maven, the ability to roll back makes it a haven. Tooling comes into play, helping to find bugs and slay, detect hidden changes before they break, catch them early before the mistake, differences in sizes of APKs, dependency diffs across the days. A central team controls dependencies, setting the versions and avoiding redundancies. Let's not forget compatibility to binary and source, to name a few. Using the tools and being aware helps save us from lots of despair. Unfortunately, that is all the time allotted for this summary rhyme, written with 0% GPT. Now go enjoy sessions and coffee. If we're okay on time, I have one more slide but it's kind of a little bit off topic in the sense that it's more related to the iOS side of things, but I thought it was worth sharing it here. So today, actually, with the same setup, the teams actually have their own shared KMP dependencies. So for example, the food team has a shared library that they share with iOS, or more than one actually shared KMP library. And the recommendation typically from Kotlin and JetBrains is to build sort of an umbrella framework, which is kind of like one iOS framework with all the KMP code in it. This has problems at scale because you end up having a lot of namespace clashes, for example. So whereas in Java and Kotlin we have packages, iOS does not directly have packages, right? So if you have a utils class, and in com.a.util and com.b.util, one of them gets renamed to util _. Also, to make things a bit more tricky, if you have the same exact class, Kotlin class, in framework A and in framework B, they're not compatible. even if it's the exact same class, because the binary representation is different. And so the choice that we end up having is you have this clashing umbrella approach, or you have what we've named the KMP tax. And what the KMP tax we refer to is the size of paying the standard library, the size of the standard library for every KMP framework we have to pay this tax. And similar for things like coroutines. Let's say we're using coroutines, every library, every KMP library that uses coroutines has to pay the cost of the cost in terms of size, IPA size on iOS for the Kotlin standard library, coroutines, and so on and so forth. We actually opt for the framework tax because it's a lot easier. And it's a lot easier with the way that we're developing, especially, we said we're split across so many repos. So you can imagine that if we were to try to build an umbrella, it would be very difficult. We can make it work, but then anytime you needed to patch something or roll back something, it would be a nightmare. But also you can imagine that one of the things that this entails is that in order to have these kind of KMP libraries, you need a bridge between the SDK, this SDK that we showed earlier, the thing that takes in the dependencies provider and does things. You need some sort of bridge between the dependencies provider type thing on Android and iOS. And on iOS, you have to build that once for every single framework. It has to be duplicated for every framework, either by moving it into iOS main or by code generating it directly. So that's it.
Thank you.